In this lecture, we're going to discuss linear systems of equations. We're going to start out with some material from your textbook and then switch over to some reference material that I have taken from various different sites. So I just think it's stated a little more clearly in other places, and I like the order in which it's presented a little bit better, but essentially we're covering sections 2 and 3 of Chapter 7 in your textbook on linear algebra on systems of equations. We all know about systems of equations. They're encountered really from high school on. A common application of matrices is the solution of systems of linear equations. So what do we mean when we say system of linear equations? First of all, linear means that we have first power terms only in x. We have a set of equations with different variables, and so in this particular example, the x subscript 1, x subscript 2, all the way to x subscript n would represent different variables, just like x, y, z would represent different variables. The a's are the coefficients, so this would be the coefficient, a11 would be the coefficient on x1 in equation 1, a21 the coefficient on x1 in equation 2, and so on. Those are known as coefficients. It's worth saying that the a's themselves don't have to be either real or numerical. They can be actually expressions in their own right. They can be complex, they can be rational numbers, they can be rational expressions. The b's are just constants, and if the b's are all equal to 0, then we refer to this system of equations as a homogeneous system of equations. What makes them linear is that you have only first powers of x, or first powers of your various unknowns in the equation. In this particular example, we have n unknowns and m equations. So a solution of the system of equations is a set of numbers, x1 through n, that satisfies all m equations. And a solution vector is just a vector x whose components would form a solution. If the system is homogeneous, in other words, if the constants are all equal to 0, then it's always going to have at least one trivial solution, meaning all of the x's or all of the variables are equal to 0. In matrix form of a linear system, we basically can accomplish this. It's like multiplication in reverse. A linear system of equations can be written using matrices and matrix multiplication. It would be written as a matrix A multiplied by a matrix X is equal to a matrix B. A is comprised of the coefficients and is referred to as the coefficient matrix. So it would be an M by N matrix. X is basically your set of unknowns. It's a vector or column matrix of length n, and B is your set of coefficients, a column matrix of length m. The augmented form of the matrix can be written as shown. When we refer to an augmented matrix, we put the little tilde over the A. That just tells us that this is a matrix for a system of equations and that it has been augmented. The difference, as you can see here, it's essentially the coefficient matrix joined by the column matrix B of the solution constants on the right-hand side of the equation. Now, the augmented matrix is unique because it contains all the given numbers that appear in the original system of linear equations. So what that means is that we can use the augmented matrix to solve the system of equations. The most common method of solution is Gauss elimination. Gauss-Jordan elimination is very similar, takes things just one step farther, but they basically build upon each other. This gives a way to solve a linear system of equations by basically reducing the coefficient matrix to a triangular form and using substitution to solve for all of the unknowns. So I'll back up a little bit and go to some different resources to go over some of the concepts of systems of linear equations. Here is basically repeated what we had before. We have n unknowns, we have m equations. Once again, these coefficients and unknowns are real or complex numbers. You can see integers, rational numbers, as well as polynomials in the coefficients as well as in the unknowns. So it could be actually quite an abstract and complex system of linear equations as long as your x's are linear. So as an example, and this is a very simple example containing unknowns x, y, and z. So our previous x1 would be x, our x2 would be y, our x3 would be z. So this is a system that has 3 equations and 3 unknowns. We find a solution to that by a number of ways. This one's fairly simple. You could use a series of algebraic manipulation and substitution to solve for this in a relatively straightforward way. It might be easy for you to see that you could add these 2 equations, eliminate y, and then just do some other manipulation to solve by substitution. The word system means that these equations are to be considered collectively and together rather than individually, and they usually represent physical things. And the best example that I can think of in an electrical engineering class is if you're writing a set of equations, for example, a set of node voltage equations or a set of mesh current equations. You will often have unknowns, voltages V1, V2, V3, or currents I1, I2, I3, or both. And so as long as we're working with linear systems or linear circuits, then we often generate a set of linear equations in currents and or voltages. Though this is just a physical illustration that shows you that an equation in terms of x, y, and z represents a plane in three-dimensional space. And if we're finding a solution to a set of equations, basically when we have 3 variables and 3 unknowns, the point of intersection of those 3 planes, the one place where the 3 planes intersect, form a solution. So this brings up the interesting case that you could, for example, have 2 parallel planes, in which case you would not have an intersecting point, and in fact that would be a special case where you don't have 3 independent equations. Okay, well, all of the essential information in a linear system can be recorded very compactly in a rectangular array called a matrix. So here's an example of how to write the coefficient matrix. It's very helpful to order things in the same order, so note that each equation goes x1, x2, x3. And then what you can do is just read directly 1 minus 2 and 1. That's going to go in the first row of your matrix. 0, 2, minus 8 will go in the second row of your matrix, and so on. So the coefficient matrix can be generated by inspection. The augmented matrix, as we've said before, you would add the column that contains the constants from the right-hand side. So this is for the previous set of equations. Notice that we've added this final column that represents the right side of the equation in the system of equations. So this is our augmented matrix. A less common way of doing things is to write what's known as a vector equation. This is also a way to represent the linear set of equations, except in this case, notice that we've written it a little bit differently. We basically have isolated our unknowns, our x1, x2, and so on, and then each one of those is multiplying a column vector of coefficients. The thing that makes this sometimes useful is that in this case the unknown can almost be viewed as a weighting factor of a column of coefficients. And so in some applications, particularly what come to my mind are applications in image and signal processing, you might have a known set of coefficients, and then your unknowns actually end up being the weighting of those coefficients. Principal and independent component analysis, another possible application for this kind of point of view, where you have unknowns that are basically acting to weight vectors. Oops, let me go back, sorry about that. So this is just a rehash of what we said before, that matrix notation. We can have a coefficient matrix, our matrix X, our matrix B, and that's homogeneous if all the B's are equal to 0, and here would be a representation of those matrices. So how do we solve a system of equations? And this is just some kind of generic mathematics. When you have a system of equations, you have three possibilities. One possibility is that the system has an infinite number of solutions. The other possibility is that the system has a single unique solution. And the third possibility is that the system has no solution. So geometric interpretation of this, if we have two equations and two unknowns, that represents the intersection of two lines. So if the two lines are the same line, then that would be an example of a system having infinitely many solutions. If they have a single intersection point, so they have different slopes, then that would be the case where you have a single unique solution. If they are parallel lines and have no intersection, that would be a case where you have no solution. Three equations and three unknowns basically represents the intersection of three planes, and n equations and n unknowns represents the intersection of n hyperplanes in an n-dimensional space. So this is kind of a unique way of viewing things. We can visualize as humans 2 dimensions and 3 dimensions. When we get to multidimensional space, it's a little more difficult for us to visualize, but in fact there are many applications of multidimensional space, and I can just give you one that directly applies to my laboratory. In my laboratory, we often record EEG signals or brainwave signals. Many of those recordings have up to 65, sometimes even 128 different sensors. And so when we get our data are a function of time, and we have 60 to 65 channels of data. That would represent a 65-dimensional space because each channel represents something unique that's being measured. So this is not as uncommon as you would think. In pattern recognition, you can have feature spaces, features that define various physical attributes of a specific problem, and you can have n of those features, and so that would also represent an n-dimensional space. So as a general rule, the behavior is determined by the number of equations and the number of unknowns. So the first point is that if you have fewer equations than unknowns, you have an infinite number of solutions or possibly no solution, and this is an underdetermined system. If you have the same number of equations as unknowns, you have one unique solution. If you have more equations than unknowns, then you have no solution, and that's referred to as an overdetermined solution or an overdetermined system. So this assumes the equations are linearly independent and consistent. So here's an example where you have a single equation. Here you have two equations and a specific intersection point. Here you would have three equations and two unknowns. So remember, this is two unknowns. So if you just have one equation and two unknowns, you can't get a solution because it's not determined, because you just have one equation. So there's no other line here that would intersect the single equation to give you a value of x and y. When you have two equations, you do have two lines, different slopes, and you do have a specific intersection. If we took this one equation and we multiplied it by, or we added a constant to it, in other words, moving it up or down, we would still have no solution because essentially it's the same equation just displaced from itself, and it will never intersect with itself because our lines would be parallel. And then here's an example of where we have three equations with two unknowns, and you can see the problem that you get these, because you have three different equations, you get these three intersection points, and so you've really overdetermined the system, so you can't get a unique solution because these three lines don't intersect in any one point. So any of these can actually form a physical dilemma when you're trying to apply linear system analysis to an actual physical problem. All right, well, let's look at some definitions. First of all, let's look at how we think about linear independence. So equations are linearly independent from one another if none of the equations can be derived from the other via algebraic operations. So in other words, we don't want to be able to divide by a constant, add a constant, do anything algebraically to be able to generate one equation from the other. Also, if we have three equations, we would not, for example, be able to take equation 1 and add it to equation 2 and get equation 3. That would not be three linearly independent equations. So we can't have anything that we can do to derive one equation from another equation algebraically or from another set of equations. A linear system is referred to as consistent if it has a solution. Otherwise, it's referred to as inconsistent. And then the rank of a matrix is the number of linearly independent rows or columns. So we're going to define something later that we'll refer to as reduced echelon form. If we put a matrix in reduced echelon form, the rank is going to be the number of non-zero rows. So basically, in a given problem, you'll have a number of linearly independent rows or columns. That would be the rank of the matrix. So here's just another visual example of two of the things that we just talked about. This first illustration here shows what's meant by linearly dependent. You can see that we have three equations here. If we take this equation, 4x plus 3y is equal to 7, and we subtract this equation, 3x plus 5y is equal to 8. So if we take the green line and we subtract the blue line, we get the red line. And so this third equation here would be an example of an equation that's linearly dependent on the other two, because we were able to do an algebraic operation on these two to get this one. So of these three, there are only two linearly independent equations. And by the way, it could be any two. So as long as we pick only two, we have a linearly independent set. As soon as we add the third, because of potential algebraic operations that can be done on the two we chose to get the third, they're no longer linearly independent, and it is now linearly dependent. An inconsistent that has no solution. So here is that example I was referring to earlier, where you have a straight line. Equation of the line is given here, and then actually it looks like the person who did this should have made this slope negative. So I didn't notice that the first when I copied this figure. So we have two equations here. One obviously has a constant offset. They're parallel lines. They're never going to intersect, so they're not going to have a solution, so we refer to that as an inconsistent set of equations. So when we solve systems of equations, the most common methods are Gaussian elimination or Gauss-Jordan elimination. The goal here is to achieve a solution by getting your coefficient matrix in row echelon form, or what we refer to as reduced row echelon form, through the use of row operations on the matrix. So here is an example of echelon form. In echelon form, all of your non-zero rows are above any rows of all zeros. The leading coefficient of a non-zero row is strictly to the right of the leading coefficient above it, and all entries in a column below a leading entry are 0. So this is an example of a matrix that's in echelon form. Reduced echelon form is in row echelon form, and every leading coefficient is 1, and it's the only non-zero entry in its column. Elementary row operations are what we use to change the matrix around so that we can get this into echelon form or reduced echelon form. And there are basically three. The first is you can interchange the position of any two rows. The second is you can multiply any row by any non-zero scalar. And the third is you can add any row to a scalar multiple of another row. So this would also include multiplication of -1 by -1. So in other words, multiplication of one row by -1, so subtraction of one row from another. So basically here are the solution steps. You take your system of equations and you put this into an augmented matrix form. and then you use row operations to obtain row echelon form, which is Gaussian reduction, or reduced row echelon form, which is Gauss-Jordan. So let's look at an example. So here's a system of equations. And so the first thing we do is we take our system of equations, illustrated here on the left, and we represent it as an augmented matrix. And the main thing we want to focus on is we're going to focus on the square part of the matrix, putting it in row echelon form. So the goal, remember, is that in the first column, we want the remaining rows to have zero coefficients. So we need this -3 and this -2 to go away. So we need to figure out how to make that happen. So just looking algebraically, we can see that if we take our second row and we add 3/2 of our first row, that we will zero out that first coefficient. So this row now represents this row with 3/2 of this row added. So that gives us our first term of 0, and then 1/2 and 1/2. And notice here that we're having to do the same operation to the augmented portion of the matrix. That's what makes this work. Making the third row go to 0, we note that if we take row 3 and row 1 and we add those, the 2 and the -2 will cancel. So that was relatively straightforward. So that's our first step. Now, our next column we need for this second column element in the last row to go to 0 so that we formed a triangular matrix. So when you do that, you want to be sure that you don't do any operations that change row 2. So you only want to do operations that are going to change row 3. And I want to make this one 0, and I want to be sure I leave this one 0. So logically, if I tried to do operations with row 3 and row 1, then I have the possibility that this first element of 0 might be made something non-zero because row 1 has a non-zero element. So it makes a lot of sense then to work only with rows 2 and 3 in order to make this happen, because row 2 had a 0 here. So no matter what I do, addition-wise, I'm adding or subtracting 0, and so I'm not going to change this first 0 that I already have, which is a good thing. So what I want to do is I want to make this 2 go away. I have a 1/2 here, so if I subtract 4 of those from 4 of the second row from the third row, I can get 0 here, and here's what shows up in the rest of the matrix. Now, if you plug this back in, you'll see that this -1, if our unknowns are x, y, z, this -1 basically only multiplies z. So this last row would be 0 times x plus 0 times y minus 1 times z is equal to 1, which by inspection tells you z is equal to 1, or -1. The second row is going to tell us that 1/2 y plus 1/2 z is equal to 1, but we've already solved for z, so we substitute for that and we can get y. Then we work our way up to the first row. We've already solved for y and z, so we substitute those and we can solve for x. So that's what's meant by putting it in echelon form or triangular form and then doing back substitution. Now you can continue this process and we can put this in what is known as Gauss-Jordan form. And so what we're doing now is we're trying to get the matrix to where it is a diagonal matrix with only ones. So I will not go through line by line each algebraic operation required to do this. I'll let you just do this by inspection on your own. But basically we do 3 more operations, and what we've now achieved is we have a diagonal matrix of 1. So now what this means is this matrix, if we were to put this back into algebraic form, this would be x plus 0 equals 2. This would be 0 plus y plus 0 equals 3. This would be 0 plus 0 plus z equals -1. So you can read directly now from the augmented column of the matrix what your solution is for x, y, and z. So if you go a couple of additional steps, you don't have to do that back substitution. Now some of you may have solved linear systems of equations using Cramer's rule. Cramer's rule basically calculates the determinant, and we'll do a little on determinants in more detail in a later lecture, but I'm assuming most of you know what a determinant is. A determinant basically takes the coefficient matrix and forms a determinant, and so notice in the denominator of each of these solutions for x, y, and z, we have the determinant of the coefficient matrix. When we solve for x, we take the column of coefficients that multiplies x and we replace it with the column of constant coefficients on the right hand side of the equation. So you can see up here for x we have our 5, 7, 8 in the column that corresponds to multiplying x when we have a matrix multiplication operation. And then the y coefficients and the z coefficients are left alone. This bottom factor, the coefficient matrix, is sometimes referred to as delta. And notice that it's the same for both x, y, and z. In y, we have substituted our right-hand side constant vector for our y coefficients. And in z, we've substituted that same vector for our z coefficients, leaving all other coefficients in the equation the same. So this is a methodology of solving a system of linear equations that you've probably seen before. The only issue with Cramer's rule is that it can sometimes be unstable, and so that's something that gives the Gauss-Jordan elimination technique a little bit of preference over using Cramer's rule. Cramer's rule is almost always good for a 3x3 or less. But when you get higher order matrices or more complicated coefficients, sometimes Cramer's rule is not the best way to go. Well, the Gauss-Jordan can also be used to invert a matrix if it is invertible. So what do we mean when we say a matrix is invertible? The matrix A is invertible if you have a matrix B, such that if you take A times B, that is equal to B times A, and the outcome is the identity matrix. So the identity matrix, remember, is just a square matrix that has zeros in the off-diagonal elements and 1 in the diagonal matrix. So when you have a matrix A that's multiplied by the identity matrix, the result is the matrix A. So how to find the inverse of a matrix? Basically, when you are given a matrix A, what you want to do is you want to augment the matrix with the identity matrix. So here is that step. Here's our matrix A, and here's the identity matrix. Now what we want to do is we want to use Gauss-Jordan elimination, and we want to reduce this original matrix A to reduced row echelon form. And what we want to do is as we do each operation, each row operation, we're going to do the same operation on this augmented identity matrix. When you've completed that process, what you'll find is now you have the identity matrix appearing on the left and some other matrix that's the result of all of those operations appearing on the right. So you can show that if you get the identity matrix on the left and this other matrix on the right, this other matrix is actually the inverse of the matrix A. Not all matrices have an inverse. If they do have an inverse, the Gauss-Jordan method is a relatively easy way to find that. That concludes this lecture on linear algebra techniques involving systems of equations. We will talk a little more about inverse matrices and why they're significant in some future lectures, but for now, that concludes this part of the linear algebra lectures.